Problem 3 is the painting demo. Here, the task is to create a program that uses a room class. The objective is to calculate the paint needed for a room based on its dimensions. This problem highlights how to encapsulate data and behavior, use private methods for internal calculations, and provide controlled access to computed results. Let's look at the requirements for the room class. The constructor must take parameters for length, width, and height. The class needs fields to store the calculated wall area and the number of paint gallons required. Crucially, these calculations must be performed by private methods. This is a key point for encapsulation and abstraction. The calculation logic is hidden inside the class. Read-only properties are required to access the room's dimensions, area, and gallons, ensuring that external code can get these values but cannot change the calculated area or gallons directly. The problem also specifies the calculation rules. A room has 4 walls, no windows, doors, or ceiling are painted, and 1 gallon of paint covers 350 square feet, with an extra gallon for any remaining area. Here is a solution for the room class. Fields. We see private fields for length, width, height, area, and gallons. These store the room's dimensions and the calculated values. Constructor. The constructor takes len, width, and height. Inside the constructor, after assigning these values to the private fields, it immediately calls compute area and compute gallons. This is important. The calculations are performed as soon as the object is created and has valid dimensions. This ensures the area and gallons fields are always up to date after instantiation. Properties, encapsulation, and read-only. Look at the properties. Properties like length, width, height, area, and gallons have only a public getAccessor. This makes them read-only properties. This is excellent encapsulation. The internal dimension values are accessible, and the calculated area and gallons are exposed, but external code cannot set the area or gallons directly, preserving the integrity of the calculations performed internally. Private methods, abstraction. We have the compute area and compute gallons methods. Notice the private access modifier. This hides the implementation details of how the area and gallons are calculated from the outside world. This is abstraction. The logic for compute area calculates the area of the 4 walls, 2x length x height plus 2x width x height. Compute gallons uses the compute area result and the gals per ESC-FT constant, 350, to calculate the gallons, correctly adding an extra gallon for any remainder using the modulo operator %. The toString method provides a convenient string representation of the room, including its dimensions, area, and required gallons using the read-only properties. The painting demo class with the main method shows how to use our room class. It creates an array of 8 room objects. In the first loop, it instantiates each room object using the constructor with varying length, width, and height values. This demonstrates creating objects with initial state. In the second loop, it iterates through the array and prints details about each room. Notice how it accesses the dimensions, area, and gallons using the read-only properties, rooms.length, rooms.area, etc., and calls the toString method. This shows how the encapsulated data and computed values are accessed from outside the class via its public interface, properties and toString. Our final problem involves creating a student record class, or simply a student class, to represent student information for an institute. The objective is to design a class that holds student data and provides ways to calculate their academic performance, focusing on properties with validation. The requirements for the student class are: it needs to store the student's ID, string, name, string, and 3 separate scores for 3 subjects, decimal. These can be instance variables or auto-implemented properties. A constructor is required to initialize all 5 of these values upon object creation. For the instance variables, properties with both get and set accessors are needed. A crucial requirement here is validation. For the subject scores, if a negative value is passed to the setter, the score should not be changed. This is an important application of encapsulation to ensure data integrity. Additionally, two methods are required: getAggregate to calculate the sum of the three scores, and getPercentage to calculate the percentage based on the aggregate and a maximum possible score given as 50. These methods encapsulate the calculation logic. Fields. We see private fields for student ID, student name, score 1, score 2, and score 3. These hold the student's data. Constructors. The code provides multiple constructors. The requirement stated a constructor that initializes all 5 values. The constructor taking string ID, string name, decimal score 1, decimal score 2, decimal score 3 fulfills this requirement. The other constructors show flexibility in creating student objects with partial data, initializing the rest to default values, like 0 for scores or empty string. Properties with validation, encapsulation. We have the public properties for student ID, student name, score 1, score 2, and score 3. Student ID and student name use simple getSet. However, look at the setters for score 1, score 2, and score 3. Each setter contains an if value greater or equal 0 check. This is crucial encapsulation. The code using the class can attempt to set any decimal value, but the setter validates the input and only updates the private field if the value is non-negative. This protects the object's state from invalid data. Methods, abstraction. We have the getAggregate and getPercentage methods. GetAggregate simply sums the 3 private score fields. GetPercentage calls getAggregate and performs the percentage calculation based on a maximum of 50. These methods encapsulate the calculation logic, hiding the details of how the aggregate and percentage are computed from the user of the class. The toString method provides a comprehensive string representation including the ID, name, all scores, the calculated aggregate, and percentage, making use of the getAggregate and getPercentage methods. Finally, the main method in Student Record Test demonstrates how to use the student class. It creates multiple student objects using different constructors, showing the flexibility in instantiation. It then prints their details using toString. A key part of this test is shown towards the bottom. It updates student 5 score 3 to a valid value, 40, and then attempts to assign a negative value, student 5 score 2 equal -10. By printing the object's state after this attempt, the main method demonstrates that the validation in the setter works correctly, the negative score is ignored, and the score 2 value remains unchanged. This confirms that the encapsulation and validation logic in the properties are functioning as intended. That concludes our walkthrough of these C# OP practice exercises. We've seen how to apply principles like encapsulation through properties and private methods, manage object creation with multiple constructors and chaining, ensure method robustness with input validation, and implement value equality. Practicing with these concepts is key to writing well-designed, maintainable, and robust object-oriented code.